Hi, welcome to another lecture. This is lecture number 18. The topic for today is the so-called L'Hopital rule for calculating limits. Why do I have a picture of a hospital here? L'Hopital in French means the hospital, but in this case, it's the name of a person. It's the first man to write a calculus textbook, actually. You can read more about this on our book, in our book, but try to learn how to spell this L'Hopital. You can also spell it with an S, like L hospital, like that. But anyway, these are rules for calculating limits of quotients. This is basically the last one of the tools that we're going to learn for computing limits, in particular limits of this form. So they are tools that help the computation of limits of the indeterminate forms 0 over 0 or infinity over infinity, by which I mean it could be either plus or minus infinity for both of them. Could be like plus in one and minus in the other. But it's also going to help us with other indeterminate forms like 0 times infinity, infinity minus infinity, as long as you're able to convert them to the ones above, to the ones as quotients. And other forms like involving exponents. We're going to see one example of this, which if you take a log, I should not say logarithmic differentiation, by the way, that word should not be in there, by taking logs, like logarithmic techniques is a better way to describe this, then you can convert those to limits of the form 0 times infinity, which then can be converted to the quotients. We're going to see how. But what are the L'Hopital rules? There's an informal statement that I'm including here that's going to suffice for us. It's going to be enough. Although the way that it's written here, it's actually technically wrong. We'll mention just one example, but most of the time, basically all the time, this is how we're going to think about it. So you have A, it's some number where you're taking a limit, or it could also be plus or minus infinity. So like this could be a limit at infinity. And then suppose that you're trying to find the limit of a form f over g, and you find an indeterminate form 0 over 0 or infinity over infinity. What does that mean? One of the following two options actually happens in here. F and g are both going to 0 in the limit, or f and g are both going to infinity forms in the limit. So far, the examples that we've seen that involve this required you to factor something from both of them and then do some cancellation so that it does not stay in this form anymore. Well, now we're going to learn this rule that takes care of basically all of those cases. As long as f and g are differentiable, you can find this limit by finding another one, which is f prime over g prime. That's the L'Hopital rule. And by the way, the same rules apply for one-sided limits. It doesn't have to be x going to a, it could be going from the left or from the right as well. So just be careful. Don't confuse this with the quotient rule. Okay, we're not taking a derivative of the quotient f over g. We are literally just putting a prime on f and a prime on g. This is not how you find the derivative of f over g, right? That's not the quotient rule. But just for some reason, which we'll discuss briefly in the end, it works if you do this. Substitute f with f prime and g with g prime and compute this other limit instead. So let's see some examples. Problem. Verify that the L'Hopital rule can be applied to the following limit and then compute it. So imagine that somebody gave you this limit, x is going to 2. If you try to compute the separate ones of the denominator and numerator, look at this one. If you plug in 2 into this polynomial, you're going to get a 0. Similarly for the denominator, 2 minus x will give you a 0. So this is a limit of the form 0 over 0. Right now, the only techniques that we know that would handle this one would be trying to factor, right? Somehow you need to find a factor of probably x minus 2 in the numerator, which is not so easy to do because it's a cubic. But well, now we can do this in this way. The two functions, the numerator and denominator, they are differentiable because they're just simple polynomials. And if you apply primes to both of them, so let me already put the primes, the derivatives. X cubed becomes 3x squared, x squared becomes 2x, minus 9x becomes just minus 9. And then downstairs, only the minus x term has a derivative, it's minus 1, a non-zero derivative, right? The 2 becomes 0 in the derivative. So this limit now is one that we know how to find because it's not indeterminate anymore. You can plug in the x equals 2, and you're gonna get this number 7 over minus 1. So minus 7. L'Hopital is just the statement that the original limit is equal to this one. It's as simple as that. But you have to be careful that you cannot immediately apply L'Hopital to any fraction. It has to be an indeterminate form, 0 over 0, or infinity over infinity. If it's not indeterminate, then that's okay, right? Like if this was a number and this is some other number that's not 0, then that's the answer, like 7 over 2, for example. You don't need to apply any special rules here. But because it was indeterminate, you can apply L'Hopital and it works. This limit is minus 7. So this is what we're going to be doing today. Here's the next one. Verify that L'Hopital can be applied to the following limit and compute it. So the verification, it's fine if you write it just directly like this, instead of writing each one of the two limits separately to verify that both are 0. You can write it like this is equal to 0 over 0. Just check it, right? If you plug in -3, what happens to the numerator? That's a 0, minus 3 plus 3. And what happens in the denominator? So -3 squared will give you 9. 9 minus 8 is 1. So you have 1 minus root 1. That's also 0. So this is the verification right here. This is 0 over 0. What does that mean? It means you can now apply L'Hopital. We're going to substitute each one by their derivatives. So maybe I'm going to indicate the derivatives here so we know what we are doing. Now we're going to need to find these derivatives. The one at the top is very easy. The derivative of x plus 3 is 1. And the bottom, that's going to require a chain rule. So derivative of 1 is 0. Then there's the minus sign. I'm going to keep those just so we know what we are doing. And then derivative of root of x squared minus 8. So the square root, the derivative of that, you may have memorized it by this point. It is 1 over 2 times square root. So I'm doing it in here, the derivative of the outer function applied on the inner function. This term needs to be multiplied by the derivative of the inner function, which is 2x, the derivative of x squared minus 8. So now you have a limit of this form, 1 over minus, let me cancel the number 2, x divided by root of x squared minus 8. What do we do with this? Okay, well, I'm going to bring the minus outside of the limit. And I'm going to multiply, well, I'm going to replace the fraction in the denominator by its reciprocal. So it is square root of x minus 8 divided by x. This is just simplifying the expression. And now this one is not indeterminate anymore. You can plug in -3, giving you, so again, 9 minus 8 is just 1, minus 1 divided by -3, that's 1/3. So this is the original limit. One thing that you should know about L'Hopital that we're going to mention in the end is that if by any chance you found a limit here after doing L'Hopital, limit that did not exist, that does not necessarily mean that the original limit does not exist. It might, and we're going to see an example, but most of the cases that we're going to see in practical life on exams, you find a number here. So whatever number you found, that's also the answer to the original limit. In this case, this one. So yeah, this is a limit that we knew how to solve already with techniques from before, like multiplying by the conjugate is what you would do. Try to do it that way just to check that the answer is 1/3. Next one, verify that L'Hopital can be applied and computed. we have ln divided by cosecant. And notice this is a one-sided limit. It's from the right side because ln would not be defined on negative numbers. But the limit of ln as x approaches 0, you should know this is negative infinity. Just remember that the graph of the ln function looks like this. So when you are here on the positive side of the x-axis and approaching 0, the values of ln are getting more and more negative towards negative infinity. And what about cosecant? So I'm just checking that L'Hopital can be applied. Well, cosecant is the same thing as 1 over sine. If x is going to 0 from the right, sine is going to 0, but also from positive numbers. This is sine x. Let me do a better job drawing this graph. It goes to 0, but using positive numbers. So this limit right here is 1 over 0 with a positive sign, and that's plus infinity. So this is just verifying that the limit is of a form infinity over infinity. It is, as I said before, the two infinities have different signs. One is minus, one is plus, but that doesn't matter. If this is still an indeterminate form, L'Hopital can be applied. So the limit is equal to same limit, 0 plus, but now you have ln prime divided by cosecant prime. Let's see what happens. The derivative of ln is 1 over x. Derivative of cosecant, that is minus cosecant cotangent. This is one that you're not likely to have memorized, but you can always find it because cosecant is 1 over sine. If you're trying to find this derivative, you can use a chain rule or a quotient rule. You should be able to get minus cosecant times cotangent. So now we have this limit to work with. Let's try to simplify that to see what's actually going on with this limit. In particular, the denominator. You have, I'm going to put the minus sign in front. Maybe you're already in front of the limit itself. Cosecant is 1 over sine. Cotangent is cosine over sine. So the whole thing is like this, cosine over sine square, which now I'm going to write as the reciprocal fraction. So you really have sine squared divided by x cosine. This x came from the 1 over x in the numerator. Oh wait, all right, now so this is limit here. What happens with it? How do we analyze this one? Well, if you try to plug in 0, you can see that this is still 0 over 0 because of the sine and the x. So technically you can apply L'Hopital again. It's 0 over 0, you can do L'Hopital, but we don't have to. We can also just split it like this, just see that this is a combination of limits that we already know. Right, I'm gonna leave one of the signs together with the over x, and then the other is sine over cosine. This one is okay. We know the limit of sine x over x as x goes to 0 is 1. Meanwhile, the other one here is giving you a 0. X is going to 0, so sine is going to 0, cosine is going to 1. You can write it like that. In any case, this is 0. So it's your choice now. When you reach this point, you can solve it very easily like this, or try L'Hopital again. Try to do that to see that you're still gonna get a 0. But this is the answer to the original limit. By the way, this limit that we always use, sine x over x equals 1, you can do that by L'Hopital. I'm gonna do these ones by L'Hopital here. So we've talked about this one, right? This is another one of the fundamental trig limits that we should remember. I hope you remember what this is. We're gonna now find it using L'Hopital. So this limit in item A, first of all, try to plug in 0. What do you get? 1 minus 1 is 0 divided by 0. It is of the form 0 over 0. So you can use L'Hopital and take a derivative of both. See what happens. So cosine is going to become a minus sign. And then the x prime in the denominator is a 1. So limit of minus sine x, as x is going to 0, well, minus sine of 0 is 0. That's the original limit. This is all. By the way, this is the answer that we remembered, right? This fundamental limit of the cosine function is 0. A more interesting one is actually this one, where you divide by x squared. What's going to happen now? So once again, x is going to 0. Once again, the limit is of the form 0 over 0, so it's okay to apply L'Hopital. And what do we get? So differentiating, cosine x gives you a minus sine x. X squared gives you 2x. All right, now when you look at this one, once again, we can just calculate this very easily because we know sine x over x as x goes to 0. But maybe let's not apply that this time. Maybe we forgot about that rule. And we're now just looking at this limit from the point of view of L'Hopital, and let's try to decide what to do. This is 0 over 0 still. If you plug in x equals 0, you're getting 0 over 0. So we can apply L'Hopital again. Let's do that. Just to indicate what's happening, I'm now going to take primes on both numerator and denominator. Sine x prime becomes cosine x. There's an extra minus sign though, so minus cosine. And then divided by 2. X prime is 1. So what is the answer here? Now if you plug in x equals 0, cosine x becomes 1. So minus 1/2. This is the original limit. Okay, what happens? What is actually happening in here? Try to imagine the functions cosine x minus 1. It look around 0. It looks like this. This would have been cosine x. If you subtract 1, then it just actually looks like this. It goes through 0. And then we're dividing that by either x or x squared. Both of the functions go to 0, right? Cosine x minus 1 and x, for example. Both are going to 0. When you divide one by the other, it's like you're trying to compare them one to the other and trying to understand what happens. In the first case, we find a limit of 0. So that means even though the two numbers in this fraction are trying to go to 0, they're trying to win against the other. The one that wins is the one in the top, because the fraction becomes small. So 0 indicates the fact that the limit is 0 indicates that the fraction is a small number. So when you divide this expression cosine x minus 1 by x, cosine x minus 1 is small compared to this x. But when you divide it by x squared, so now there's more power in the denominator. This time they don't become, one is not like much smaller than the other. They are comparable this time because you found a number that's not 0. It's minus 1/2. So this time they are actually comparable in size. Just try to imagine what the x squared function looks like. It's the parabola. The two graphs are very similar together. And one over the other is approaching the number minus 1/2. So we're going to come back later to this idea of comparing different functions. And more specifically, we're going to be doing that as x goes to infinity later. But let's move on right now. Here's an example where x is going to infinity. Once again, we're going to do this by L'Hopital. So x is going to infinity, and this is a ratio of polynomials. You can guess what the answer is going to be because we know it's going to be 3 over 2. Those are the two highest degree terms, and they are of the same degree. So the answer is just the ratio of the coefficients. And we know that we can get to that by dividing by x squared, both numerator and denominator. But the point now is not to do that. The point is to use L'Hopital. So first of all, the limit that we have, what form is it? Answer, infinity over infinity. Because as you take x to infinity, because they are polynomials, only the highest degree term is the one that determines what's happening, and both are going to plus infinity, right? The highest degree terms are both positive. So this is indeterminate. You can apply L'Hopital. So we can do that. Taking the derivative will give you 6x minus 5 divided by 4x. Okay, let's not even think about this. Let's just try to plug in. That is still infinity over infinity. Both 6x and 4x are going to infinity. So we can do L'Hopital once again. By the way, you might want to get into the habit of writing a little LH on top of the equal sign whenever you're applying the L'Hopital rule, just to indicate what you're doing. So, and to further indicate it, maybe I'm going to write the primes first before I actually compute them. How does that look now? Well, 6x prime is 6, 4x prime is 4. Now this is the limit of a number. It is just the number. And the number is equal to 3 over 2 after dividing by 2. Just like we had guessed, right? So L'Hopital works in here. As you can see, it's not that hard. But now we're going to get into some ones that are not actually quotient forms yet. This is an indeterminate form of a product. Compute this limit, x times ln x. X is going to 0 from the right. So as x goes to 0, this first function x is going to 0. What happens to ln x? We've talked about this earlier. It goes to minus infinity. This is an indeterminate form, 0 times infinity. This could be anything. L'Hopital, now, it does not apply directly to this. L'Hopital applies to quotients, 0 over 0 or infinity over infinity. We need to, first of all, transform this into a quotient. Let me erase this. So when you have a product like this and you want to transform it into a quotient, what you do is you take one of the two functions, usually the simpler one. So let's take the x, and you rewrite it in the denominator as a reciprocal, so as 1 over x. We're going to say this then. This limit, ln x here, is equal to, so ln x remains in the numerator, but x goes to the denominator as 1 over x. This is still the same function, but now it is of the form infinity over infinity. Right? We already knew that ln x is going to minus infinity, whereas the function 1 over x, if x is positive but very small, well, that is a positive but very large number, so it's going to infinity. And if it is infinity over infinity, we can do L'Hopital. So let's do that. So we're going to take the derivative of ln x, that is 1 over x. Actually, let me indicate that first. Ln x prime and 1 over x prime. The derivative of ln is 1 over x. The derivative of 1 over x, you probably memorize this one. It's minus 1 over x squared, because that's just x to the minus 1. So by the power rule, it becomes minus 1 times x to the minus 2. Okay, so we have this limit now. Well, if you just plug in 0 here, you see that you're getting still infinity over infinity, but you should not immediately try to apply L'Hopital again. You should simplify this as much as possible before you take any conclusions, draw any conclusions. In this case, you have fraction over fraction with an extra minus sign, so let's write the minus outside. And let's write the 1 over x squared as x squared over 1 multiplying. You see that the x's will cancel with the minus sign outside. We have now just x. And the limit of x is 0. So this is the answer, just 0. Let me just go back to the problem. I want to once again point out to what's going on. So we were looking at the expression x times ln x, as x is going to 0 from the right. So the function x is this one, it goes to 0, and the function ln x is this one, goes to minus infinity. And we're multiplying the two of them, x times ln x. Well, x is trying to go to 0, so it's trying to make the product small. And then ln x is going to negative infinity. It's trying to make it large in size, but also negative. Which one is going to win? That's the question. Which one is more powerful as x approaches 0? And what we're finding out is that x is the more powerful one, because we found that the answer to the limit is 0, just like where x was trying to take this product. So even though ln x is trying to become very large in size, the smallness of x more than compensates for that, and the product just becomes 0. So once again, trying to understand such expressions as comparisons between two functions. Indeterminate forms can always be thought about it in this way. And finally, we have one example here involving exponents. This is going to be a special one, by the way. It's a limit that we should remember for future reference. 1 plus 1 over x to the x. And x is going to infinity. First of all, why is this indeterminate? What's happening is that the base is going to 1. 1 over infinity is 0. Is going to 0, right? So only this 1 outside is left. So you have a base going to 1, but the exponent is going to infinity. So the limit is of the form 1 raised to infinity, and this is indeterminate. Once again, because of this competition between two functions. On the one hand, the function in the base is trying to get closer and closer to 1, and 1 raised to anything is always 1, right? So the base is trying to make sure this expression is small. But on the other hand, the exponent is larger and larger, and when you raise a number that's larger than 1, such as this one, to larger and larger powers, you keep getting larger and larger numbers. So this could be anything. It could be a very large or very small number. We have to determine this somehow. It's going to be L'Hopital, but the way that it's written, we don't have a quotient yet. In fact, we have what's called the Taylor function. You have x both in the base and in the exponent. So you know that what you have to do here is take a log. What do we mean by that, though? How do we take a log in a limit? This is the procedure that you do. Call it something, maybe L. L is the limit that you want to find. What we're going to find first is the logarithm of L. ln L is equal to limit of ln of the expression. So I had written logarithmic differentiation, but then I crossed out the word, remember? There is no differentiation here. We're not taking primes yet. We're just taking log of the original expression for the limit. And now, what do we do? Okay, so ln L, this is the limit that we're going to find. How do we find this one? Well, the whole point of the trick is that because you had an exponent, after taking a log, it is now going to move to the front, like this. And okay, what is this expression now? X is going to infinity. Let's work this out carefully. If x is going to infinity, this x here is infinity. And what is this logarithm? Well, 1 over x is 0 because x is going to infinity. 1 plus 0 is 1. And then ln of 1 is 0. Infinity times 0. This is what we have. Indeterminate. All right, infinity times 0, just like before. This is two functions. One function is trying to get very large. The other function is trying to get very small. Which one is going to win? Or maybe they don't win, actually. Maybe this cancels out and gives you a number, whatever number that's going to be. It's not actually 1/2. We'll have to see that. We have to use L'Hopital to find. to find out what this number is. Okay, but we've just done an example like this where you have infinity times 0. You have to first convert this to a quotient, remember? So what I'm going to do is I'm going to take the simpler function, which is the x function, and move it to the denominator as a 1 over x. Because now this is infinity, sorry, in this case, this is 0 over 0. Right? We already knew this, the limit of the ln here was 0, and now because x is going to infinity, 1 over x is going to 0. So 0 over 0, indeterminate, and something that you can apply L'Hopital to. I once had a student who said L'hospitalize. You can L'hospitalize this function. So let's do that. Let's take the primes. This is not as nasty as you think it might be. You just have to do this very carefully. So in the numerator, you're going to require a chain rule for that, definitely. You have log of something. So the derivative of the log would be 1 over the inner function, 1 over 1 plus 1 over x. We need to multiply this by the derivative of the 1 plus 1 over x, the inner function. That is a minus 1 over x squared. So chain rule gives you this for the derivative of the numerator. Denominator is easier, that is just minus 1 over x squared, the derivative of 1 over x. We've done this earlier today. And you can see that the minus 1 over x squares go away immediately. So you just have this limit that you don't need to simplify anymore because this is not indeterminate. Try to imagine what's happening here. As x goes to infinity, 1 over x goes to 0. So this is a 1. As I said, this infinity times 0 up here, as it turns out, these two functions, the way that the x goes to infinity and the way that the ln of this expression goes to 0, they are at approximately the same rate. They're doing in such a way that they cancel each other out, and the answer that you get in the end is a number, not 0 or infinity. It's just 1. Okay, however, this is not the final answer. We're almost there. Let me just go back. If you go back through your chain of equalities, you will remember this is not the limit L that we wanted. This was ln of L. That's the whole point that you need to remember when you have tower functions like this in a limit. ln L is equal to 1. So what is L actually? Just take the e in both sides, e to the 1. If ln of something is 1, then that thing is e. This is the final answer. So in a lot of calculus textbooks, the definition of the number e is going to be as this limit, by the way. We've never actually given a definition of this magic constant e. It can be defined by using this limit, and then the properties of e, like the derivative of the exponential function, for example, they all derive from here. You can try this on your calculator, by the way. Take a very large number x, calculate this 1 plus 1 over x. That's going to be a number larger than 1, but not by much. And then raise that to x. What you're going to find is something that's very close to e. So the final answer here is e. So yeah, L'Hopital is just going to require lots of practice. You have to practice as many problems as you can, but it's not really that hard. It's just showing you yet another use of the derivative. What I have now in this last slide is I want to mention an informal proof. Why does this magic trick work? We should be aware of that. It should be, it may help you consolidate this idea in your mind. So here's an informal proof. It's not a formal proof. You're going to see why. So suppose that you have two functions that are differentiable. And suppose that you're trying to find the limit of f over g, and you find a 0 over 0. You find an indeterminate form. Let's not discuss the case of infinity over infinity. That's more complicated. So this is now why this is an informal proof, linear approximation. If you remember linear approximation, close to this number a, the functions should be given approximately by these formulas. Right, this is something that we studied recently. Well, because the functions are continuous at a, we know that because they are differentiable. Differentiable implies continuous, remember? Then whenever we see f of a, we know that that has to be equal to the limit of f of x as x approaches a. This is the definition of continuity right here. And on the other hand, this limit, we were assuming that that's a 0. This was assumed up here. When we say that the fraction f over g is of the form 0 over 0, what we mean is that the limit of f is 0 and the limit of g is 0. So because of continuity, we know that f of a and g of a are both 0. So I'm going to replace those up here. This 0 is f of a, the 0 is g of a. So when you compare f over g, instead of writing f of a, I'm writing 0. Instead of writing g of a, I'm writing 0. And the rest here is just the rest of the linear approximation formula. What happens? You're going to cancel the x minus a's. This x minus a is common to both of them. And what you get in the end is just f prime over g prime at the number a. The final blow now is just that if you assume that these derivatives are also continuous at a, then instead of f prime of a and g prime of a, you can write the limits. Limit of f prime over g prime as x approaches a. Once again, by continuity, which is not assumed, by the way. You don't have to assume this for L'Hopital to work. So yet again, this is another reason why this is just an informal proof. A formal proof would require more tools, something called the generalized mean value theorem, if you're curious. But if you ever go into higher level math, you're definitely gonna study this. But anyway, this is just giving us an idea. Here's once again this idea of linear approximation that I told you. We studied this also for theoretical purposes. Here's an example of how you compare two functions using linear approximation. So the formal statement of L'Hopital, if you want to state it as a theorem, this is actually how it goes. It's not going to be extremely important for us to know this. The way that we were just applying it will be fine, but you should be aware that this exists. Mainly the difference is that you have to assume that the limit that you get with the primes exists. So I'm going to read this. Suppose you have two functions differentiable on some interval containing the number a. Suppose that g and g prime are never 0 around this number a. So when x is different from a, they should not be 0. This is just technicalities, right? This is here because we are considering fractions where g is in the denominator. So we can only do that if we know that g is not 0. Now suppose also that the limits of both f and g are 0. This is the part that tells you that the limit of one over the other is of the form 0 over 0. So I'm not even stating what happens if it's infinity over infinity. Instead, this is why I'm saying one of the L'Hopital rules and not all of them. But anyway, so we're assuming all of this. Then what happens? If this limit with the primes exists, then the original one with f over g also exists and is equal to the same one that you get with the primes. So that's the important part. The important part right here. It's saying the limit that you get after you put the primes, that one should exist. If it does, then you can conclude something about the original one. If it doesn't tell you anything. So in particular, that's the last box here. If you after you apply the rule, if the limit that you get actually does not exist, you cannot conclude that the original does not exist either. Maybe it does. And I have one example. Here's the example. Analyze the limit x going to infinity, 2x plus sine x over x by L'Hopital and also directly. So by L'Hopital, if you look at this limit, what happens to both numerator and denominator? x is going to infinity, so the denominator is going to infinity. That's easy. Same thing is happening on the numerator. Even though sine x does not have a limit as x goes to infinity because it keeps oscillating, but the dominating term here is the 2x. That one is going to infinity. So it is infinity over infinity. You might want to apply L'Hopital here. You can. This is the part that's gonna fail now, though it's not actually equal. We're gonna see why. So what happens if you do L'Hopital? Derivatives of 2x becomes 2, sine x becomes cosine, and then x becomes 1. So what is this limit here? Limit of 2 is 2, and limit of cosine as x goes to infinity, this does not exist. That's the problem right there, the limit of the cosine. Once again, because cosine is oscillating between -1 and 1 forever. It doesn't go to any specific number as x goes to infinity. So that's a problem now. If after you apply L'Hopital, you find the D and E, that does not mean that the original limit does not exist. So it doesn't mean original limit D and E. In fact, the original limit can be evaluated directly. Let's do that. This was the original limit. What we should do here is divide by x. We have both terms in the numerator are divided by x, so let's implement that. What you actually have is 2 plus sine x over x. And now what is this? Okay, 2 is just going to 2. Where is sine x over x going? If you said 1, be careful because this is not a limit as x is going to 0. That one goes to 1 when x goes to 0. But this time x is going to infinity. That's actually a 0. So the 2 is just 2, but the other one is going to be a 0. Not so hard to think about why. What's happening is sine x is always oscillating between -1 and 1. But so it just stays bounded. It stays within 2 specific numbers. But then the x in the denominator is getting larger and larger, trying to bring this fraction down to 0. And there's nothing in the numerator to counteract that. The numerator is well behaved if you want to think about it that way, but the denominator is going to infinity. So the fraction is going to 0. As you can see, then the original limit actually existed. It was equal to 2. Even though after you apply L'Hopital to it, you get something that does not exist. So you just need to be aware of this. If you find a D and E after L'Hopital, that doesn't mean anything. But those examples are very rare. So yeah, I think this should be all for today. In the recitation about this topic, we'll do many more examples of L'Hopital. In particular, examples like this one where you have tower functions or also products that need to be transformed into quotients first.